Welcome to Ask and Learn.
In this problem, we're looking at the area of a circle, and we're finding average rate of change for various increments, changes in the radius, starting with the radius change from 2 to 3. And anytime you're looking for an average rate of change, you're just using a basic slope formula. So if the radius is changing from 2 to 3, what we want to do is find the area for a radius of 3 minus the area for a radius of 2 and divide that by 3 minus 2. That would be our slope formula. So we end up with the area for a radius of 3 is pi times 3 squared, so that would be 9 pi. And the area for a radius of 2 would be pi times 2 squared, so that would be 4 pi. And we're dividing that by 1, and so we get 5 pi. For the second part, we're finding the rate of change, the average rate of change, as the radius changes from 2 to 2.5. So same idea, the area for 2.5 minus the area for 2 over 2.5 minus 2. And the area for 2.5 is 6.25 pi, and the area for 2 is 4 pi, and we're dividing that by 0.5. And this gives us 4.5 pi. We're going through that process one more time, and the radius is changing from 2 to 2.1. So we have the area for a radius of 2.1 minus the area for a radius of 2 over 2.1 minus 2. And that gives us 4.41 pi minus 4 pi over 0.1, and that works out to be 4.1 pi. Okay, so for part B, we're finding the instantaneous rate of change when r equals 2. So we're finding a prime of 2. First, we need to find a prime of x. And remember, a of x was the area of the circle. I should call it a of r. Pi r squared is the area of the circle. So its derivative would be 2 pi r. So then a prime of 2 would be 2 pi times 2, and that would be 4 pi. Notice that our previous answers were getting closer and closer to 4 pi, the smaller our interval got. We had 5 pi, we had 4.5 pi, and we had 4.1 pi. And if our interval had gotten even smaller, we would have been even closer to 4 pi. All right, for part C, notice that the rate of change of the area is 2 pi r, and we also know that the circumference of a circle is 2 pi r. So we're noticing that those are the same, and we want to look at a geometric argument for that. So we have our circle with radius r, and it grows bigger, and now the radius is r plus delta r. So our new circle has area pi times r plus delta r squared, and our old circle had area pi r squared. So the delta A, the change in area, is the new area minus the old area. And that would be pi times r plus delta r squared minus pi times r squared. Let's simplify that. We can factor a pi out of both, and then we're going to multiply out the binomial, and we get r squared plus 2r delta r plus delta r squared minus r squared. The minus r squared comes from this last term. We factored out the pi earlier. Notice that we can cancel the r squared and the minus r squared. So what we have left for the change in area is pi times a quantity 2r delta r plus delta r squared. Now suppose we were interested in delta A over delta r. Change in area over change in time. We're going to take what we just got for delta A and divide it by delta r. And while we're doing that, let's factor out a delta r. So we have pi times delta r times 2r plus delta r over delta r. Cancel the delta r from the top and the bottom, and we have pi times 2r plus delta r. Now suppose we're looking at a very small delta r. If delta r is extremely small, then that's essentially 0, and what we have left is 2 pi r, the circumference of the circle. So if you were interested in approximating a change in area for a very small delta r, you would just approximate it by finding the circumference.